How's everyone doing? So I've thought a bit about ophttpd and what you need to do with it. And what I need to add is a static site generator. And I've concluded this. I mean, it's something I'm eventually going to have to do. And and let me very briefly outline my larger plan. My larger plan is to convert this into another project called Marketplace, and so I want to have some content. I basically want to have static sites, a blog, then some sort of microblogging thing, so sort of kind of like Twitter. Then it needs to have a chat room feature and paywalling, and I'm not entirely sure how it's all going to work together. But one thing that is absolutely going to be needed is some non-HTML markup language and a templating system. So, you know what? I should look and see if there's something in another in Erlang that's already like this. So, static site generator Erlang. Something that, because relying on something outside of Erlang. Okay. Yes. Oh, Garrett, he's always good. Okay. Let's see how this. Of course, your website doesn't work. Well, my website doesn't work either. Okay, I don't want something like JSON. It's going to be more like a, it's going to have something closer to a GUI. And so I was thinking I also just want it to be more tech-like. And eventually I want to be able to write all of my revelations in this new language. And so I think, let's see. So let's look at the templates. How do his templates work? Gay.html. Okay, let's try. Okay, here, I have a different idea, which is to basically make a LaTeX-like language. So my idea is a bit different, and I think it's actually a good idea. The more I think about it, the more I want to do it. I was just looking at the score. Man, this Rays Red Sox game was a really good game. It was a good game. Let me turn. Go away. Oh yes. Okay. And I might need to turn off the slideshow so that you can see my work. But let me. Okay. Let me call this one ophttpd. There we go. Detach. And this new thing I'm going to call, okay, let's do a, let me blow it way up. And I hope you can see this. Create project. Okay. And it is a, ooh, what is it? Maybe, I think for now it'll be in it'll be a library, and we can always convert it to an application later. So tech, and I'm going to call it TechXX. I was going to call it hypertech, so it's like tech, but it's meant to be converted to HTML. I wonder if they're here. And then there's something called hypertech already. I think that might be the hyperref package. I'm not 100% sure. And then I was going to call it techML, but that's gay. So instead we're calling it TechXX. TechXX. It's good that it's hard to say. TechXX. that name is such cancer. Let's make it MIT licensed. LaTeX-like language. Compiles. TechLite. Okay. Project repo. You know what? It does need to be a application. And the reason is because, okay, now let's just, here we go, GitLab. Oh, I have a great idea. Okay. And I have a great idea means Craig had this idea, and I'm gonna do it. New project. God damn it! How do I? New project. Here we go. So it's going to be called Text. LaTeX-like language that compiles to HTML. And I don't want to initialize the repository. Okay. That's good. Okay, and then cd text git switch git init git switch -c massa. Okay. That's not even a command. Okay, here we go. Git add doc git commit -m commit ZX create project git push git remote. You can code along with me. Oh, massa, sorry. I'm going to switch all of my projects to that eventually. That's hilarious. Okay. It's going to get me canceled off of GitLab, isn't it? Okay, so how does this need to work? Alright, first thing I guess we need to do is the lexer. Okay, the lexer or the tokenizer. So I wrote a thing, Revelations 20 on parsing, which I think we're going to reference a lot. Okay, tmux text. ESRC. Oh, here's a good one. lex.xrl. It's such fucking cancer. Okay, so can't remember how this works, so that's why I wrote Revelations 20. So, I have it on my own machine, don't I? CRC rev. Events rev. There we go. Here we are. Oh, let's see. I just want to remember the syntax. So that's right, it needs definitions, rules, airline code. Okay. And so I think, oh god damn it. So if you're not familiar with LaTeX, okay, let's do let's first just have it recognize backslashed stuff. So let's do alpha num A through Z, A through Z. Then command equals backslash alpha num plus. Okay. Then what do we want to escape? This isn't an easy language, is it? Okay. So what is our open brace is equal to, it's just this. Okay, let's just try this out. Okay, and then our rules are going to be our command is going to be, let's just write this in directly just to make sure that works. Command. So the lexer, its role, I used in the goal of the lexer and the grammar is to come up with a syntax tree, and then what you do with the syntax tree is up to you. Okay, but the lexer identifies parts of speech, and then the grammar looks at the flat list of parts of speech and chooses a tree structure. Those are the roles of the two things. Okay, so rules command, this is going to be token command token line token bars. And white space is kind of significant. Let's see. Okay, and then anything else is going to be token char line chars. Okay. And let's just test this. Okay. 10, bad rule. Oh boy, oh yeah, I remembered this. It's because it has to be lowercase Erlang code. Okay. How do we do this? Let's start with okay, C Lex. That's such cancer. Okay, Lex. String. Hello. God damn it. There we go. Oh, this is going to be such cancer. Okay, yeah, so it prints it correct. Okay. Oh, this is going to be such a nightmare. Okay. Okay. Let me look in the documentation for LaTeX. Let's try this. End of string as end token. EOF. Let's try this. Bad regexp. Mind. Okay. Let's try open brace. Open sigchar. Let's do unbs of token chars. Unbs of Does this work the way I expect it to? That's so retarded. Token, okay, I'm thinking we should have special stuff for begin and end. I really don't know. Maybe let me look up parsing tech. Maybe tech is not a... Let me look at markup languages. List of markup languages. Because now I'm thinking that here we are. There's going to be a lot. There's context. I've heard of this. No shit. Shut up. Oh, what about tech info? Yeah, I don't need, I think I'd prefer grammarable tech, I think is better. Okay. Close brace. So the braces act like quotation marks in LaTeX, if you're not familiar. Or like they're kind of parentheses in LaTeX. Okay. Let's try hello world. Alpha nouns. Let's try, does this work? Does this work? Looks like it works. And then I think for environments, yeah, okay, that's what I thought. I should probably fix WFC, shouldn't I? Let me write down a to-do list. There. Fix WFC. Oh, I don't have a to-do list. Here we are. fix WFC, or get WFC back into old form. Horizontal banner, okay, okay. To do, god damn it, to done, to do, now, to do, medium, okay. Okay, I already started the data mining playlist. Done, which was start. And the to-dones are going to go at the bottom. I don't know what this is. This is in low priority. I did look at PGF plot. Oh, this is high priority. Okay. Medium horizontal. This is low priority. This is kind of done. This is low priority. I haven't seen it. I think it took down my locals. I'm not sure. I tried to upload an image and it took down my locals. Okay, and then I think for then our quargs. How are we going to do quargs? So I think the way it's going to work is there's going to be args and quargs. Okay, maybe let me write an example. That would be better. Okay, let me write an example. That's maybe better, and then we code against the example. tech. H1. Ooh. Yeah, because I want... God damn it, there's going to be scoping rules, aren't there? Ah, this is hard. Okay, I want a tech. I don't, because I already realized tech is just a nightmare, and so I want something that's kind of tech-like. But do I even want it to be tech-like? Okay, so let's kind of maybe think backwards. Okay. How about begin HTML, end HTML, and this way, okay. Doc type HTML. Head, title, the title. QQ HTML. Quasi-quoted HTML. So maybe that's a better approach, is it assumes it's HTML and only does non-HTML things when, okay. It's a better approach, isn't it? Well, that's what everyone else is doing, isn't it? Do I want to do this? I do. I don't, but I also do. Okay. So it's going to need to have a state machine because it's going to need to know the names of variables, basically. Okay, you know what I'm going to do? I'm going to watch a YouTube tutorial on designing a markup language because that'll give me some ideas. How about this? Okay. Markup language. Let's try this. I don't care about this. This looks funny, so I'm going to click on that. Oh, this I remember being a good talk. So let's watch Brian. Brian Kernighan's probably a guy who's worth listening to. This is good. I think probably creating a real language, that might actually be interesting. Mark. Let me put, has to contain the word markup. Let's see, does that help? Let's try this. That's 50 minutes long. That looks funny, but I will. This is 4 minutes long. Okay.
HTML is a markup language that we use online, but it's not the only markup language out there. And the concept of a markup language is sometimes easier to explain when we actually look at a couple of different examples. In general, markup languages are designed to explain how text should be formatted using other text. So it's not what you see is what you get. It's instead, it mixes the content of a particular document, whether it's a text document or a web page, with instructions about how the content should look. So let me give you some examples of HTML compared with some other markup languages, because honestly, HTML, if you're writing certain types of things, HTML isn't even the best markup language to use for certain types of documents. Okay, so let's say that let's start with HTML because that's the one that we're familiar with, and let's say the goal here is that I want bold text. I want bold text. How do I get it? In HTML,
what happened?
What I'm going to do is the canonical way to do this is to use something called the strong tag. So the strong tag indicates that the contents here should be strong. It should be stronger than the text around them. And typically, browsers will interpret the strong tag as meaning this content is now bold. So if you look at this in a browser, you would see that this is bold. How about using some other markup languages? So there's something called LaTeX that is frequently used by people when they're formatting papers. So LaTeX also has a way to make text bold. Here's how bold text looks in LaTeX. I want to learn how to type. So this is interesting, right? Here I have the tag that starts with strong, ends with /strong, and the contents are in here. In LaTeX, I start a tag with this backslash, text BF, that's text boldface, this open curly brace, and then here's the contents of the tag, and then the end curly brace. So this is how it would look in LaTeX. Let's look at a couple of other pretty common text-based markup languages. There's something called Markdown, which is quite common online. You can use Markdown to write README files on GitHub and in a variety of other places. It's pretty nice. In Markdown, here's how you get bold text. Double star, I want bold text, double star. So Markdown will find the double stars in your document, determine what text in between them, and make that text bold. So this is how it looks in Markdown. Here's another example. There's another markup language that I like that's called Ascii Doc. Interesting, Ascii Doc. Oh yeah, I need to scroll down here. Let's see. Oh. Here we go. So in Ascii Doc, the interesting thing is that bold text is a little bit confusingly different from Markdown. So you'll see in Ascii Doc, the markup language has just decided that bold text is in 1 star. So here's the start, here's the end, and the Ascii Doc compiler will just figure out what parts of the document should be bold. In Markdown, it's 2 stars. So, so here's a sort of a comparison of these 4 different markup languages doing the same thing. All I want is bold text. In HTML, I use the strong tag, and I have to close it with another strong tag. In LaTeX, I start a tag using textbf in this particular case, and then these braces define where the tag goes. In Markdown and Ascii Doc, I use stars, either 2 in Markdown or 1 in Ascii Doc. Now, what's interesting about this is if you look at the number of extra characters I had to type to achieve bold text, right? So in HTML, I have strong, which is 6 characters, plus the tag is 8. Over here, it's 9 because I have to close the tag. So that's 17 extra characters I had to type to get bold text. In LaTeX, I had to type 4, 7, 8, 9, so 9 extra characters. Markdown, it was 4. Ascii Doc, it was 2. So there are newer Markdown languages, or markup languages, sorry, like Markdown and Ascii Doc, that are really designed for people to write text in. And part of their goal is to make the markup component of the text as lightweight as possible. That makes it faster to write things, and it makes the text a little bit less cluttered. And so, in general, if you're writing content for the web, I would suggest that rather than writing HTML, which you can do when you get started, find a way to write things in a better markup language, a more modern markup language, and have that be converted to HTML rather than writing it in HTML directly.
Okay, so this is intended to be a summary of some of the more obvious bits of the history of documentation markup. I'm only hitting some of the high spots. We haven't got time to go over everything. The GitHub repository has the slides, the source for the slides, and extended notes with a lot of the links I found trolling Google and spending ages. So feel free to go back there and look at that. The slides and so on are available under a Creative Commons license as well, so if you want to steal things, please do. So we've had markup of text to say what you should do with it for a very long time. Back in the days of typewriters, people would double space their text so it was easy to proofread and write marks in between. They would use underlining to mean this should be in italics. They would use
You gotta find him. Yeah, you can understand why he won the Turing Award. Oh, god damn it, it's gonna be the... Okay, I know how... I know LaTeX. I want to understand how the LaTeX compiler works. How about Terry A. Davis compilers? He has a great talk about how compilers work. Here we are, this one. I'm gonna make sure to download because Terry's stuff keeps getting taken down. I think if there's someone I'm going to learn about compilers from, it'd be Terry. I gotta download like all of... Is there a way to like download all of the videos from a single YouTube channel?
Okay, I'm going to tell you about the Temple OS compiler. So it's 20,000 lines of code. 20,000 lines of code. It has an assembler for x86, 64, and an unassembler. It's strictly 64-bit for Holy C. The assembler can do 16-bit, sort of, or it doesn't have full segmentation support. I'm trying in Temple OS to keep the number of lines of code to a minimum. It's one of my highest goals. Anyway, so a normal diagram has a stream coming from the preprocessor into the Lex, into the parser, into the optimizer, into the backend. This is the normal conceptual model of a compiler. So in Temple OS, okay, first of all, this does not generate intermediate files. I think my compiler is unusually fast. As a matter of fact, well, I haven't benchmarked, but anyway, so I don't do a preprocessor into a separate file. I don't do a stream either. Lex is a function called by the parser, and Lex has the preprocessor built in. So get this in your head. You have the preprocessor, the Lex. What the lexical analyzer does is it makes tokens. A token is the smallest unit of interest in the stream of compiled code. So if I have a compiled code,
oh my god, I gotta have Terry quotes. Okay, that's gotta be going on my to-do list. Low priority. Add Terry quotes about compilers. Revelations 20. I think I will make Revelations 20 about compilers.
For I equals 0, I less or equal to 10, I plus plus. If I have something like this, alphanumerics are combined together into a token of an identifier. This is called an identifier. Here are all the tokens. You have, okay, I have a superscript and subscript. That's, anyway, so, if you take a compiler course, you learn about the lexical analyzer and the front end. I don't think very many places teach back end compilers. I just had a front end. Anyway, so an identifier is a bunch of alphanumerics that make up a keyword or a label or something. That's what an identifier is. And the lexical analyzer puts together tokens, or it divides into tokens, I should say. So the lexical analyzer would say, okay, we have an identifier I64. It skips the white space. The lexical analyzer gets rid of white space and comments. And the preprocessor has pound include. I have my lexical analyzer is merged with my preprocessor. Anyway, so I is an identifier. Then you have a semicolon, and guess what? I don't have a token for semicolon. All the symbols, or what do you want to call them? All the punctuation marks are treated by their ASCII value. So when the lexical analyzer is a function you call as you're parsing, and it says, okay, we have a token identifier, we have a token identifier I, we have a semicolon, and it returns the ASCII of the semicolon. Then it says we have a token for, which is also a keyword, and then then it returns the ASCII of a parenthesis. Then it says we have an identifier I, and then it returns the ASCII of the equal. So if we were going to diagram this, we'd say we have token identifier, and I have a structure for a compiling control structure or something like that. Compiler control structure, and just the lexical analyzer is a function that gets one token, and it also stores the token if you want it to fetch it for later. It returns the token as the return value of the lex, and in the structure it puts the current. Oh, by the way, the numbers are converted to from ASCII to binary. That's what they call it, binary. It's kind of weird calling it binary, but anyway. So I have a spot for if it's an integer, if it's a float, if it's a string. This is from an identifier. Now you can merge together multiple identifier. Never mind. So some of the other tokens are string and oops, where did the tokens go? So identifier. This is a string that comes in double quotes, an integer, a character constant in single quotes. My compiler is unusual because I let you put multiple character constant characters. Let me just show you what I mean. If you say I64I equals quote A, B, C, D, in normal C you can only have one character, but in here we have it makes an integer by just shifting in multiple characters. Anyway, so we can have a character constant, a float. Now for the single symbol, for the single punctuation symbols, we return the ASCII. For the multiple operators, we have some tokens for that'll. So we take care of merging together two character operators, shift left, shift right, etc., etc., and you will not get the if defs. You will not see them, but internally it sees those. And we have ... binary. Okay, so Temple OS allows sprites in source code. So if we look at our demo game, so in this source code is sprites. So the lexical analyzer has to return a pointer to a binary sprite.
I think I'm going to watch this fast because I'm not going to absorb everything, and then I'm going to have to watch it again. Okay, I'm going to watch this and then I'm going to take a break. How about that?
Okay, so I just wanted to get you familiar with the lexical analyzer returns tokens. The parser starts putting together expressions. Parsing an expression with operator precedent is the hardest part of a compiler. Conceptually, they do some when they explain it. If you take a compiler course, they'll talk about left recursive, LR parsing and stuff. Don't do that. Don't do nestle. There's one thing that's ridiculous, which is if you have there's a trick. There's a technique they teach in school for parsing expressions, and what you do is you make a recursive function for each level of operator. I changed the operator precedence, by the way. I made bit shift exponential, so it's the highest precedence. It's a lot better. Anyway, so don't do that LR parsing. Instead, make a precedence integer and compare the precedence. Don't do that LR parsing. Well, if you're making just sometimes it's not important if it's good. A good compiler, fast. Anyway, so parsing, that's where you put together statements and expressions, and then optimizing. One of the main things that okay, my parser generates stack machine code. So if you give an expression like this, what it says is push 1, push 2, push 3, pop rex, pop rdx. I don't know. I'm kind of multiply rex times rdx, push rex. I'm just talking conceptually, and then push 4. And then we do I skipped a step. So you push rex, then you say pop rex, pop rdx, add rex plus rdx, push rex, push 4, and then we do the pop and add. Reverse Polish, basically. So that's the idea. I want to make an intermediate code that's my own representation of the code. So what I do is I make a stack machine intermediate code, and then in my optimization stage I substitute registers for common offsets. So local variable. I only do stack function arguments. I don't do register arguments. That's x86-64. Some people like to say it has a standard for register arguments. Well, only if you want to follow it. I get people Jedi mind tricking me. Oh, you have x86-64. That means you use register arguments. No, I don't. I don't use register arguments. And I assure you it is x86-64. Anyway, so one of the things you have to know about, you have to know assembly in order to do a compiler. And the arguments are, by the time you get to a, let's see, the stack, you have to know the stack frame. I use the old school stack frame all the time. I use the RBP stack frame, and that makes it possible to climb the stack really easily. Anyway, so
I don't even know what a stack frame is. I need to learn about this.
Anyway, so the arguments are positive off the stack, off the base pointer. I type stuff when I'm talking and I don't pay attention. It just comes out. Anyway, so the
see, is that like a compiler's course? I think I gotta watch this. This would be interesting. This video is hilarious. Gotta make sure I'm subscribed to this channel. Let's see. Some old guy is probably the best approach here. Okay. Definitely gonna watch through this course. Okay. Adding this. Oh, this is part of that course. This guy looks really short. Or his head is really large in proportion to his body. I hope he's not like a midget or something, but anyway. I'm sure he's very good. Gasan Shobaki. What type of name is that? That sounds like Pashtu or something like that. Ugh.
So what's a compiler? Yeah.
Translate source code into machine object code.
Okay, source code. And what's source code?
This actually looks good. Even though it's, I'm worried that guy might be Pakistani, and then. Ugh. Anyway,
Hello everybody. Welcome to the Language and Translator class that's being given.
French. Fuck this guy. Alright, I'll add this one as well. Let's see.
Dobro wieczór. Sometimes you just need to create a compiler. There are not many good reasons to make one today, maybe exercise. But when I made the JRPG translations, I really needed one. Compilers like GCC and Clang just do not target the 5822 that is in the Super Nintendo. Creating a compiler begins from defining the language that you are compiling.
I like this guy's weird ass voice. Let me find his playlist. Glad I found this channel. This looks really interesting. Creating a compiler. Is this what I was just watching? Yes, it is. Okay. Oh, NPTLER. Okay, as much as I hate Pakistanis, I hate Indians more. Let's see.
Okay, so what is it we're going to talk about?
We're going to talk about parsing. It's essentially the process of recognizing the shape of a particular input string. And the process of parsing comes about, it's not only a domain, it's something from computer science, but also comes from linguistics and can be generally used as a synonym to recognition or understanding some concept. And computer science is more to do with, and specifically in programming language, it's more to do with a specific component inside of what we call a compiler. A compiler is essentially a translator that translates one language, the language of the programmer, into a systems language. So a compiler needs to be able to handle inputs and have outputs. The compiler translates these, handles these two. So you have an input that is a string, any sort of text data usually. The first part in the compiler, the basic stuff that a compiler should do, is essentially parse the input. And here the string, let's say for example, needs to be able to be analyzed. And this has several steps. In order to handle the string in the best way for the system, you have lexical analysis of the string. So say you have a given multiplication, 50 times 10 equals 500. And this is a string. First, what it's going to have to do is lexical analysis. And here there's a particular reference to how humans can actually understand information. A computational interpretation, how we understand it would be to like analyze each thing. So like you have the sentence, my dad is coming home, and you classify those into verbs, adverbs, nouns, etc. What the parser does essentially is do lexical analysis, which essentially means creating tokens. Tokens are each of the elements on the string. So like 50, the multiplication sign, 10 equals 500 or so. And it needs to be able to do this because, end of the day, the string goes through a syntactical analysis. The tokens create some sort of data representation. And this data representation, in order to be able to be translated, it needs to be put through syntactical analysis. This is the part that's really interesting because syntactical analysis means, in humans as well.
Oh my god. You know what's funny? My voice here. Let's find a video. I didn't even know. I knew about Ascii, but I didn't recognize the name Harold Abelson because I don't pay attention to people's names. Or I knew of Ascii, but I had never really read it. God, I wasn't even listening to that guy. That guy was boring as shit. Okay. This old guy is not very engaged, or he's engaging, but he doesn't. All right, here. Let's listen to this guy. His voice sounds exactly like mine, except he has a super Jewy Brooklyn accent.
Today is August 23rd, 2011.
Shut the fuck up.
Computer science at MIT.
I don't care what the other guy's saying.
In central New Jersey. My parents worked on the farm. My father later went and worked in the post office. I was the first one in my family to go to college, although my parents were always very, very interested in education. My parents liked music education. I had an uncle who sort of was the college person who worked for Exxon. I'm not quite sure where I glommed onto math and science. I remember when I was, I guess, 12 or 13, I decided I wanted to be a physicist, mostly because I think I liked the word, but I did.
All right, let's I'm going to go down an autistic rabbit hole, aren't I? I've never read this book, and it's like 800 pages, and I don't want to do yet another, but I think this is, if I actually want to do this, I need to understand the way that this shit works. So I'm wondering how the hell it gets to 800 pages. Because there's only 5 chapters. And I don't think I'm going to be able to read this out loud because it's just going to be too long. I'm going to have to read it silently. Okay. $16.90. Oh. Maybe I should pair this with the SICP lectures. Okay, I wanted to subscribe to this channel, which I did. Don't need that. Let's look into this, see what this is.
Hi, this is a brief tutorial on syntax.
This guy has a faggy voice.
Let me be a little bit more precise about how we're going to represent expressions. We're going to use these classes here. So we've got a class called add, and then we build a new object. Here we're...
Yeah, I don't like that.
Okay,
Graham Hutton's always worth listening to.
Today we're going to do some more live coding, and we're going to talk about something which is quite close to my heart, because I wrote some of the early papers on it many years ago, and that's something called functional parsing, or combinator parsing.
Right.
Before we get started with actual live coding, I want to begin with a question, and the question is, what actually is a parser? So for me, a parser is a program which takes a string of characters as its input, and as its output, it produces some form of tree. And the idea is that the tree makes explicit the structure in the input string. So that's a bit of a mouthful, so let's have a simple example to explain what's going on with this. So what we've got here is we've got a string of 5 characters, 2 plus 3 times 4, and that's our input string. But when we look at this, we know that that's not just a random sequence of 5 characters, it's actually got some structure to it. So in particular, we've got 3 numbers here, 2, 3, and 4, and we've got 2 arithmetic operators, we've got the plus and the times, and one of the things we learn at school is that the times happens before the plus. So you really do 3 times 4 here, and then you add the 2 on at the end. So that's our input string. So what a parser does is it takes a string of characters like that, and it tries to recognize the structure in the form of a tree. And the tree we would get from a parser is something like this here. And you see we've got some leaves in the tree. The leaves are the numbers 2, 3, and 4. And the nodes in the tree are the 2 arithmetic operators. That's the plus symbol and the time symbol. And you can see the structure of the tree reflects the fact that we do the multiplication first. We multiply 3 by 4, and then we do the addition second. So that's the basic idea of what a parser is. It takes as input a string of characters, and as output it produces a tree. So it's really a function. It's taking an input as a string and an output as a tree. So we've seen what a parser is. It's a function that takes a string as an input and produces a tree as an output. So now we want to think, how can we actually implement this? How can we implement the idea of a parser? And I'm going to do this in Haskell today, but it doesn't matter if you don't know anything about Haskell because I'll be explaining everything as I go along. And actually, nothing I'm going to show you today is specific to language like Haskell. You can do it in any general purpose programming language. So if you do a web search for combinator parsing or functional parsing, and then whichever language you're interested in, you'll find the same kind of stuff which I'm going to show you today. So it's not specific to the Haskell setting. So what we're going to do then first is we're going to define precisely in our programming language what it means to be a parser. We're going to define a new type called parser, and it's simply going to be a function which takes a string as an input and produces a tree as an output. So it captures the very simple idea of what we're wanting to do. A parser is a function that takes a string as an input and gives a tree as an output. And the arrow here just means that we have a function from one thing into the other. So this captures the basic idea of what a parser is, but unfortunately it's not sufficient to program with. We need to refine this a little bit to actually write programs with this. So the first little refinement we're going to make is that a parser might not consume all of its input. So for example, if we're trying to parse a number, like 2, maybe we find the 2, and then maybe we've got some more stuff left in the input string that we need to parse. And if we want to chain parsers together, we're going to need to have access to the remaining input string that we didn't manage to consume. So the first little refinement that we'll make is rather than just returning a single tree, we're actually going to return a pair now. We're going to return 2 things. We're going to return a tree as before, and we're also going to return the unconsumed part of the input string. So that's the first refinement we've made. The second refinement we're going to make is that a parser may not always succeed. We may be trying to parse a number, and we don't find the number, we find something else. So we need to have a way of representing that a parser can fail. So the way we're going to do that is we're actually going to make a parser return a list of results rather than a single result. So lists in Haskell are denoted using square brackets. So this simply means that rather than returning one pair of results, we could return 0 or 1 or 2 or as many as we like. And the idea is going to be if our parser can't parse, so it doesn't succeed, we'll return an empty list of results. And if it does succeed, we'll return a list with one pair in it. We'll return a tree that represents the structure of the input string, and we'll return the unconsumed part of the input. But because we're working with lists here, we could actually be more flexible. We could return 2, 3, or 4, or 5, or as many as we like parsers. And this is actually quite a good flexibility because for some languages, the input string may be ambiguous. Maybe we're trying to parse English, and English sentences don't always have one parse. They can be interpreted in many ways. So this type here is giving us the flexibility to return many results if we wanted. We're not actually going to use that flexibility today, but it's nice to actually have it. So I haven't told you what the tree data type is here, and that's because I'm actually going to get rid of that now. Sometimes you may want to return a number or a program or some kind of other structure. So we're going to replace that specific type of trees by some arbitrary type A. And I'll make this a parameter of my type. This is our final type which we're going to work with today. What we're saying is that a parser whose results have type A is simply a function which takes a string as an input and then it gives a list of results. And each result is a pair comprising a single value of type A, maybe a tree, maybe a number, maybe something else, and then an unconsumed part of the input string. Okay, so this is our final type. And if you look at any of the articles or books about these kind of parser combinators or functional parsers, you'll find the type very similar to this there. It's quite a mouthful again. So let's think about how we can understand this in a simpler way. And actually we can write a little rhyme to understand what's going on with this type. So let me write the rhyme out for you as a comment. So what we can say is a parser for things is a function from strings to lists of pairs of things and strings. This is a little Dr. Seuss rhyme to tell you what a parser is or what a functional parser is. And that's actually how I remember this type. So that's our basic type now. We've seen so far.
God damn it. A parser for things
this is a little
is a function from strings to lists of pairs of things and strings. Okay, and so why do you want to do this?
Dr. Zusrein to tell you what a parser is, or what a functional parser is. And that's actually how I remember this type. So that's our basic type now. We've seen so far a parser is basically a function from strings to trees, but in order to actually program with these kind of things, we need to refine the type a little bit, and this is the type we'll be working with today, but you don't need to worry about the details of it, just basically think it's a function from strings into trees, or some other kind of structure. What we're going to do now is we're going to load up the parsing library, so I'll start up the compiler. This is a library which contains a whole bunch of parsing stuff, which allows us to program with parsers of this form. And this is a parsing library I wrote myself. I'll see if I can get Sean to upload it as part of the video. A parsing library comes with any programming language you can think of. Again, if you just search for parser combinators functional parsing, whichever language you like, you'll find a library which gives you all sorts of basic ways of building parsers, and that's what I'm going to show you now. All of these libraries work in the same way. So you have some basic primitives or basic building blocks for parsers, and then you have a way of combining parsers to build bigger parsers. So it's like a kind of Lego kit or a construction kit. You have some basic bricks that you can do things with, and then you can put those bricks or components or primitives together in all sorts of different ways. I'm going to show you a few of the primitives and a few of the combining forms, and then we'll do an example. The first primitive I want to show you is very simple. It's just a way of parsing a single digit. So what the digit parser does is it takes a string of characters and it tries to consume a single numeric digit off the start of that string. Okay? And you might think, well, what does parse do here? What parse does is it takes a parser, which in this case is just digit, and it takes an input string to that parser and it just applies one to the other. So of course this parser here is going to succeed because we do have a digit at the start of the input string. So we get exactly the expected result. We get a list with one pair. And the first thing in the pair is the actual digit. We get the character 1. And the second thing in the pair is the unconsumed part of the input. And that's something we can then try and parse subsequently.
I understand
we can test this thing fail properly. So if I give it an input string that doesn't have a single digit at the start, then it's going to fail. So if I give it the input string ABC, there's no digit at the beginning, so we're just going to get the empty list of results. So I'll show you one more quick primitive. If I parse a single character, say an A from that string, then that will do the right thing. If I parse single character A and I didn't have any at the beginning, then it will fail. Okay, so we've seen two basic parsing primitives here. We've seen a way of parsing a digit, a way of parsing a specific character, and we've seen that these things can succeed or fail. And in the library or in any of these libraries, there'll be a bunch of these basic building blocks or basic bricks or primitives that you can use to build up your parsers. Where things get more interesting is when you think, how do you combine these kind of things? How do you use these basic bricks to build actually useful parsers? Let me show you an example of this. So there's a parsing combining form called sum. And what it does is it takes a parser as its input and it tries to apply it one or more times, as many times as possible. So if we're trying to parse some digits, what we're trying to do is consume one digit, then two, then three, and as many as we can until we don't find any more digits. Okay? So if we apply the sum digit parser to the string 1, 2, 3, then it will do the expected thing. It will consume all three of the digits, and then we'll get the empty string left here. So that's sum. It gives us a form of repetition. We also have a very simple way of making a choice as well. So if I want to make a choice here between a digit and a letter, and let me parse the string ABC, 1, 2, 3. So what we've got here is this funny symbol here, with the three symbols. That's a choice operator. It says do that or do that. So if I try to parse a digit or a letter, what it's going to try first is it will take the first character in the input string and say, is it a digit? If so, I'll parse it. And if it's not a digit, then I'll go over to the other side and say, is it a letter? And I will try and parse that. You can see what's happening with this particular example here. If I look at the first character, it's not a digit, it's a letter. So when I apply the digit parser, it would fail. And then the OR operator, or the choice operator here, will go over to the other side and say, well, is it a letter instead? And of course it is. So we can parse the single A off the front here, and then we get everything else as unconsumed. And of course, if we want to be a bit more clever, we can combine some of these things. So I could say sum, digit, or letter, get my brackets right, ABC 1, 2, 3, and then that will parse everything. Because all I'm doing here is I'm repeating or iterating the choice between either parsing a single digit or a single letter, and I've got a string of digits and letters here, so I can parse the whole thing, so I'll consume them all, and then I get nothing left at the end. So what we've seen so far is some basic building blocks, and we've seen a couple of combining forms. We've seen a way of doing repetition, which is sum, and we've seen a way of making a choice, which is the funny operator in the middle there. What I haven't shown you so far is how to do some form of sequencing. And this is the most common thing you typically want to do with parsers. You want to say, do this, and then do that, and maybe do that as well. You want to sequence things together. So I'll actually show you a bit of the parsing library here. So here's the parsing library, and I don't want to go through all the details of this, but one thing I want to know is it's quite short. If I kind of scroll down here, it's about 4.5 screenfuls, and I've got quite a big font here. And this is actually already quite a sophisticated parsing library. So it shows you the power of this method, that you don't need hundreds of lines of code to write parsers. 4.5 screenfuls is a library which is fully fledged, and you can basically implement any parser you like using this. So I'll show you a couple of examples of sequencing. The first example I want to show you is a parser for natural numbers. So what's a natural number? It's just a non-negative integer, like 0, 1, 2, 3, or 10, or something like that. So you think, how do you parse a natural number?
Well, proprietary. Fuck him. Never mind. Let's try this. I don't give a shit about that. Okay. Of course it's they managed to make Erlang look like fucking Haskell. Alright.
Lines. Some I'm rather proud of.
Okay, I don't have time for that.
use the sequencing notation for parsers, which is the do notation. And the do notation is very simple. You write the word do, and then you have a whole bunch of parsers, one after the other, and it just runs them each in sequence. So the first thing here is we're going to parse some digits, because that's the basics of what a natural number is. It's just some digits. And if that succeeds, I'm going to call all those digits x's. So x's is just going to be a list of all the digits. And then what I'm going to do here to be a bit more flexible, probably when I parse a number, I don't want a string of characters back. I actually want the number. So I'm going to pass the string in to a little function called read, which just converts the string into a number, and then I'm going to simply return it. So the basic idea here is we're sequencing two things together. We're reading some digits, or parsing some digits, and then we're translating those into a normal number, and then we're returning it. And we're sequencing those things together using the do notation here. So just one more little example, because we'll use this in a minute. Here's how you could parse an integer. So an integer is either a negative number or a positive number. So there's a choice there. So we're going to use the choice operator. So here's the OR operator, which we've seen a few minutes ago. And the two parts here just say, have we got a negative number or have we got a positive number? So the parser for a negative number, we use the do notation because we need to do three things. So the three things are here. So if we're trying to parse a negative number, the first thing we do is we parse a minus sign. So we're using the char primitive that we saw previously. That will parse a minus sign. Then we're going to parse a number and call it n. And then we need to remember that we need to make it negative, so we negate it, and then we return it. So again here, we're just using the simple idea of sequencing three parsers, one after the other. And then the OR here says, or we can just have a simple natural number. Okay, so this illustrates the idea of sequencing. And if you've seen some of my previous videos, you may recognize the do notation here. And this is because parsers form an example of what's known as a monad. And in fact, for me, parsers being monadic is one of the key ways to understand what a monad is. So if you've seen the monad video, or even if you haven't seen it, maybe have a look back at that. And if you find it interesting, maybe look up some of the work which people have done on monadic parsing. It's a really good way to get a very good feel for what's going on with both these kind of parsers and monads as well. We've seen that parsers are basically functions. We take a string as an input and produce essentially a tree as an output. We've seen some basic primitives for consuming single digits and single characters and things like that. And we've seen some basic combining forms. We can have repetition with sum, we can have choice, and we can have sequencing. So we've got our basic kind of building blocks for making larger parsers. So let's wrap this up now by doing a little example. An example I want to do is to build a really simple parser for the kind of expressions or arithmetic expressions that we saw back at the start. So things like 2 plus 3 times 4. So what I'm doing here is I'm writing a Haskell program which is going to implement this parser. What I've got in the first line here is simply importing the parsing library, which we've just seen. It's just 4.5 pages of code. It's very straightforward. And what we've got here in the comments is a simple way of writing down what the syntax or form or structure of expressions are. And this is what's known as a grammar, but it doesn't matter if you don't know what a grammar is because the basic idea is very simple here. The first line says an expression can be one of two things. So this means or here in grammars. So an expression can either be a term plus an expression, or it can be a term. And then in turn, a term can either be a factor times a term or a factor. And finally, a factor can be a bracketed expression or an integer. So there's three simple rules here which explain the form or structure of what a simple arithmetic expression can be. There's actually quite a lot of things going on here, but the only key thing I want to point out is we've got three rules because there's three different levels of priority in an expression. So the highest level of priority is brackets. So that's one thing you learn in school. You learn that you do the brackets first. That's the highest priority thing. The middle level of priority here is multiplication. So that's sitting in the middle rule. And the lowest level of priority is you do addition. And that's sitting at the top rule. And again, this priority order is something you learn at school. You do brackets first, then you do multiplication second, and then you do things like addition last. And these three rules are just making that precise. But again, if you want to know more about grammars, you can search on that and you'll find lots of information about that online. So what we want to do now is take this little grammar and implement it as an actual parser. And this is very straightforward to do because we're using this functional parsing idea. Essentially, we just take those three grammatical rules and we just implement them using the combining forms and the primitives that we've seen. So it's a very straightforward translation. So the first one is we want to say an expression can either be a term plus an expression or a term. So let's do the first part of that. So we've got term plus expression. So what we're going to do is parse a term, and if that succeeds, call it x. Then we're going to parse a plus character. Then we're going to parse a expression and call it y. And then we're going to return x plus y. So there's four things going on in sequence here. We're first of all parsing a term, then we're parsing the plus character, then we're parsing an expression, and we're getting the values here, x and y, these will be numbers, and then we're going to simply add those two numbers together. So you can see here we're actually doing more than just parsing, we're actually evaluating the expression as well. And that's one of the advantages of this approach to parsing, that it's not just about building a tree, you can actually process things as you're going along. And we're actually processing them here by doing complete evaluation. So x and y will be numbers, which result from this term and this expression, and then we just add them together here and return the result. Then the last part of parsing an expression is we can either be a term plus an expression, or we could be a term. So we just use the choice operator, and we get a term. And these 5 lines here are our full parser for expressions. So we had this one rule up here, an expression could be a term plus an expression or a term, and we just translate it directly into our parsing notation. And again, the key observation here is that the grammatical rule here is basically the same as the parser. So let's look at the second rule.
I really like the way this guy explains it. He's really straightforward and direct, and I mean Haskell is just
in fact, it's pretty much the same as the first rule, except a few symbols are changed. So let me just copy it, and I can just change it. So I can say a term can be a factor times a term, and then I can do a multiply there, or I get a factor. Okay? So just a few key presses, I've managed to implement my parser for terms. And again, the point to note here is that the grammatical rule here looks basically exactly the same as the parser. Okay? I've just got a few more symbols in here because I'm actually writing a program to do parsing, or actually evaluation, but it's the same basic structure. And then just to wrap things up, I can implement what a factor is. So a factor is either a bracketed expression or it's an integer. So let me write the parser for that. So a bracketed expression, I just parse a character, and then I parse an expression and call it x, and then I parse a closed bracket, and then I return the x, or I can parse an integer. And again, if you look at the structure of the rule up here, a factor is a bracketed expression or an integer. I've got exactly the same thing down here. Here I'm parsing a bracketed expression, and here I'm parsing an integer. And this is actually our entire parser. We've got 3 lines up here, and we've just got kind of 10 or 15 lines down here. And this is actually a complete parser and evaluator for arithmetic expressions. And again,
so the reason I don't like Haskell is all the hidden context swaps.
The beauty of this approach is the parser looks basically the same as the grammar. So let's try and see if this works, and hopefully I haven't made any mistakes. So let's load it into the system. Okay, that's great, no errors. And we can see that we've loaded 2 files in now. We've loaded the parsing file in, which is that 4.5 pages of definitions, and we've loaded the example program in now. So now we can check does our parser actually do what we want. So let's try out our parser with the little example that we had at the start, 2 plus 3 times 4. So we're going to parse an expression, and the expression is 2 plus 3 times 4. And we press return, and we hope we get the right result, and we do. So remember from school, you do the multiply first, you do the 3 times 4, so you get 12, and then you add the 2 on at the end, and you get 14. So we've managed to get the result 14 here, and there's no portion of the input string left. So we've got a successful result, we've got a list, and we've got one result value, we've got 14, and we've managed to consume the whole thing. And we could check, does this actually work with more sophisticated examples? So let's try putting some brackets in. Let's put brackets around the 2 plus 3. So we get 2 plus 3 times 4. So we hope then that we do the addition first, and we get 5, and then times by 4 to get 20. Yes, and it works. We can try more sophisticated examples, so let's do something like 2 plus 7 times 10 plus 8 times 20. And if I've got the brackets right, yes, then it works fine. We can also check what happens if you give it something which doesn't parse. So suppose I do do something like a parsing expression, so 2 plus 3 times, and I forget to write 4 at the end, what's going to happen? Well, the parser will still manage to succeed because it will manage to parse the 2 plus 3 and we'll get the 5 out, but it doesn't know what to do with this symbol sitting on its own. So you get that back as an unconsumed part of the input. And again, we can try another example. Suppose I forget to close the brackets, so I do something like 2 plus 3, and I forget to close the brackets, then it won't know what to do with that at all, and we'll just get the empty string. That's basically it. This is the idea of functional parsing, or combinator parsing. The idea is very simple. Parsers are basically functions. You define a library with some basic building blocks, or primitives, some combining forms that let you put these things together, and then you can end up writing parsers, as we've seen, that look very similar to the grammars that you write to describe languages.
The man goes to town, as we would say. To town, the man goes. Sounded to me 20 years ago when I first stumbled on this very much.
I think I watched this a while ago.
Hi and welcome to the first session of the Building a Parser from Scratch class. My name is Dmitry Soshnikov and I'll be teaching this class. And just to set the agenda, this is purely a practical class. Right, we'll have just a few amount of theory in this class related to parsing, but most of the videos will be actually practical exercises, building a parser from scratch. And we'll be building a parser for a full programming language similar in syntax to Java or JavaScript. And for those of you who are interested in a more deeper theory for parsing and parsing algorithms, you may consider also the Essentials of Parsing class, where we discuss in detail all the parsing algorithms such as LL, LR parsing, etc. And we also build
all this stuff looks important.
I actually think that if we're going to do parsing, it might be easiest not to dive into compilers straight away, some of you might want me to do, but to actually just take a simple, very simple subset of the English language and see how we would parse that. And if you look up in a dictionary, what does parsing mean? It says, essentially, one of the definitions is breaking up sentence structure into its component parts under the direction of a grammar. That is the rules of your language. Well, I have drawn up here a language involving fairy dice and robots and people, men and women, and cats and dogs, and they can bite, they can stroke, they can whatever. And I thought, the grammar, which I'll walk you through, is typically generated between 200 and 300 sentences. And they are all valid.
I think I've watched this one before.
I could have said, but I'm going to do it as subject can be an article followed by a noun.
No, I get this. That's Revelations 20. I wrote all that shit. Okay.
In computers, that you understand the string, understand the sentence, let's put it that way. Why is this important? Because semantics, meaning the actual outcome, what it means to understand a sentence, comes out of syntax. And syntactical analysis is basically done through a reference to context-free or any kind of...
Alright, I know, okay. Parsing, I think I'm solid on.
Railta. One of my previous work is a ROM hack, the fan translation of Chrono Trigger, a famous JRPG by Square. One of the features that sets my translation apart from nearly every other fan translation in the world is its ability to conjugate names. English is a language where most of the grammar is accomplished by adding small extra words called prepositions. These prepositions have no meaning by themselves, but they express a relationship with respect to another word. English prepositions include words like at, on, from, to, in, and so on. However, my ROM translation is to my native language, which is Finnish. Finnish language does not really use prepositions. Instead, it uses a principle called conjugation. In conjugation, the word itself is treated as a malleable object that changes shape depending on the situation. For example, the Finnish word for daughter is tytär. However, to say my daughter, we would say tyttäreni. It is important to note that this is not just tacking suffixes into a word. The word itself changes its shape. The conjugation rules in Finnish are extremely complex, and Finnish is actually said to be one of the most difficult languages in the world to learn, at least if your native language is English. It is just so different. I mean, look at this family tree. Finnish is not even in the same tree with English. Languages like Russian and Greek are closer to English than Finnish is. To be honest, there are other languages that have complex conjugation rules, but very few languages have as many grammatical cases as Finnish does. This poses significant challenges to computer software developers and localizers working with one of these languages. For example, in a video game you would typically have somewhere a message that says something like, you found one horn, you found one feather, you found one mop, you found one star sword. This is generally implemented by a pattern rule, where there is a blank slot for the name of the item, but the rest of the sentence is fixed. This approach works poorly in Finnish. If we translate the pattern literally, we get the following sentences. Löysi yksi sarvi, löysi yksi sulka, löysi yksi moppi, löysi yksi tähtiniekka. And this is just wrong. Anyone who knows Finnish can tell. This kind of sentence, the item name should be conjugated in the accusative case. Löysit yhden sarven, löysit yhden sulan, löysit yhden mopin, löysit yhden tähtiniekan. But the item names might come from one list that is used everywhere in the game, including the player's inventory. If the names were in accusative cases in that list, the inventory would look totally wrong. The item should be listed in the nominative case, not in the accusative case. There are a couple of approaches often taken by translators to solve this problem. One way is to rewrite the sentence in such a way that the nominative case does work. For example, yksi sarvi löytyi, yksi sulka löytyi, yksi moppi löytyi, yksi tähtiniekka löytyi. But this often requires changing the word order, which is not always possible. Also, it no longer says you found this and that, but this and that was found. The translation is no longer accurate. The other option is to add a scapegoat, a label that gets the conjugation treatment, leaving the template parameter untouched. Löysit yhden esine nimeltä sarvi, löysit yhden esine nimeltä sulka, löysit yhden esine nimeltä moppi, löysit yhden esine nimeltä tähtiniekka.
The scapegoat here is the word esine, meaning item. This is proper grammar, but again the translation is not accurate. It now says you found one item for them all, not you found one more. This approach is commonly used in computer programs where the scapegoats are words like file, folder, user, address, and so on. It lets into cumbersome language, but it is an acceptable compromise. But in an RPG, where you can change the player character names, none of this will work. In Chrono Trigger, before the game starts, you will give a name for a main character. This name and names of other characters you can name are referred to everywhere in the game. Using the cumbersome circumventual expressions would be inappropriate for the atmosphere of the game. In Chrono Trigger, I made a system that automatically conjugates any name that the player might enter. It is not based on hard-coding the conjugated forms of names in the table, because the player can enter any name they want, and there are about 10 different conjugations that are used throughout the game, for every name. Instead, the conjugation rules, they're written in a special scripting language that I made for just that purpose. It is extremely limited and really only suited for rudimentary string operations. My inserter tool would interpret this script and translate and compile it into assembler code and inject it into the game ROM. Thus, the game would correctly conjugate almost any name that the player might enter in real time on the SNES console according to the Finnish grammar rules. Later, I reused this same system in Tales of Fantasia 2, and that's what I did 15 years ago. Man, time flies. Today, if I wanted to do this, the script would look very different. I would probably do something like this. The syntax is a sort of mix between C and JavaScript programming languages. Because a lot of you folks have never written a compiler, I thought it would be nice if we went through the process step by step. Mind you, I have never taken a course in compiler design, so what I do might not be the same as your average university course. It is probably going to be interesting. This will be a video series in which we will go step by step through the process of creating a simple compiler for this made-up programming language covering the whole system, from language design through optimization using different intermediate representations into
I like this guy.
Hopefully then running it. The primary tools and languages that I will use will be C++, GNU Bison, and RE2C. Subscribe and click the bell icon to receive notifications whenever I publish new episodes. Now, I am planning to use the 360-degree video technology that you can see in this video. You probably already realized it, but on a desktop computer you can wrap the camera around by holding the left mouse button and zoom using the scrolling wheel. Let me know in the video comments whether you like it or not. See you soon again.
Wow, that's cool. I didn't know about that. God damn it.
Sometimes you just need to create...
One.
Who are these people?
One of my previous work is a ROM hack, a fan translation of Chrono Trigger, a famous JRPG by Square. One of the features that sets my translation apart from nearly every other fan translation in the world is its ability to conjugate names. English is a language where most of the grammar is accomplished by adding small extra words.
Dobry wieczór. Sometimes you just need to create a compiler. There are not many good reasons
to represent.
This looks like a good, anyway. This I'm gonna have to... Okay, I'm gonna pick one of these and watch it. I'm not gonna watch this guy. This guy I'm sure is good, but this number one, the French accent, is really hard to hear because I want to watch at 2x speed just because I'm impatient.
This description. Our treats.
And the French accent I have incredible difficulty with even at normal speed, and so I think and the PowerPoint type is less engaging for me, so I'm going to go ahead and not... I saved it. This guy, I don't like the Finnish accent. I actually didn't really have trouble with it. I thought I would have a lot of trouble with it. This guy, I like. This guy seems like a Terry A. Davis type, except I don't think he's a schizophrenic, crazy guy. This guy looks good. It's MIT, so it's gonna. And he's white, so he's probably gonna be at least decent. I mean, the newer stuff at MIT is garbage, but.
The following content is provided under a Creative
Oh, this is part of the other playlist. Okay, so. the chalkboard lectures aren't as good for me as here. I think I will go with Terry and this guy for a little while.
A parser in that class uses parsers. In general, we differentiate the handwritten parsers and automatically generated. Expression, multiplication, and so the right-hand side is the identifier y. Okay? So the purpose of the parser again is to function, or what this grammar rule derives.
I like this guy. I like this guy for having a lot of practical experience. Okay. I'm writing something much simpler than this, but my aspirations long term require me to learn this, and this seems like a rabbit hole that I can't afford to go down. But just because I'm kind of crunched for time, but at the same time I kind of do need to go down it. I'm basically spending, an hour to automate 5 minutes of work. It's more than that. I'm spending like a week more. I mean, for every 5 minutes of work doing HTML, I'm spending a week, but it will pay off. I know that. So I should watch this one about the history of text markup languages. I hate this guy. Fuck this guy. I mean, he just seems like a dick. And didn't he like scam a bunch of his followers or some bullshit like that? Anyway. Let's see, this guy. Oh yeah, I love this guy, this Biscuit guy. Oh, this looked funny. Let's see.
So, what's your VS Code? What is your theme name in VS Code?
Custom VS Code themes. Everyone wants one, but if you've ever tried making...
I don't even fucking use VS Code. Yeah, I don't actually give a shit about this.
In the last video, we talked about its unique syntax. Then, we defined single character tokens. We also defined character...
Is this another Indian guy? Oh my god, it is. Ugh.
Character, integer, and floating point values. From here, we start getting more generic into array identifiers, and strings. When a line feed character, which is the backslash...
This guy looks like he's going to give really clear explanations, so I like this. Oh wow, this guy's good. This is nice. Okay. I like this guy's channel. I don't like that he's Indian, but I'll deal with that. Where did he have time? This shit's good. No, this is basically shit I wanted to talk about. Okay, where is his compiler playlist? Does he have... God damn it. Does he have a playlist for this video? Playlist. Damn it. Create programming language. Motherfucker. Am I gonna have to assemble a playlist myself? How many videos are there in the playlist? Alright. That guy, I like his channel, so I'll subscribe, but... yeah, okay, Brian Kernighan's a really... okay. This will be to watch later. Write the down. Okay. This is a good talk. I've watched this before, but I want to watch it again. This guy looks good. Alright.
Uppercase letters and underlining to say this should be a heading and so on. I'm going to cover... Okay, so this is intended to be a summary of some of the more obvious bits of the history of documentation markup. I'm only hitting some of the high spots, we haven't got time to go over everything. The GitHub repository has the slides, the source for the slides, and extended notes with a lot of the links I found trolling Google and spending ages. So feel free to go back there and look at that. The slides are still on our videos, there's under Creative Commons license as well, so if you want to steal things, please do. So we've had markup of text to say what you should do with it for a very long time. Back in the days of typewriters, people would double space their text so it was easy to proofread and write marks in between. They would use underlining to mean this should be in italics. They would use uppercase letters and underlining to say this should be a heading and so on. I'm going to cover some of the technologies that have been used in the computer environment since about the 1960s. One of the interesting things is that many of these are still being used. I'm not quite sure what that says, but, and I've used quite a few of them myself. So in background, I started programming in the early 1980s, so I've seen quite a bit of history. And this talk just came with me talking to colleagues and them saying, well, you should write this down. There's lots to cover. I'm not going to get through everything. We'll see where we get. There are basically two types of markup that we can see people doing, presentational and semantic. The presentational markup is just saying, when you present this text, when you draw the text on paper, screen, or whatever, it should look like this, it should have this appearance. And semantic is saying, the meaning of this text is such and such. Now, actually there's a realization fairly early on that those two can be combined. It's worth saying, this is a header, this is a list. This is not just draw me at 17 points in dark black. So there is an overlap there. I have one format I talk about which is purely semantic, but mostly things are somewhere in between. Separate to that, and independent, we've got two other concepts that we'll come across. One is lightweight markup, where you're not having to, where you can concentrate on the text. The actual markup you put in is a background task, it's not very obvious. And the other is perhaps the possibility of programmable texts, where your actual text is a program, you run it, and you get a document. And that may sound odd, but you'll actually find you already understand that when we get to it. So even at the very beginning of our timeline, though, people had quite sophisticated needs. We had phototype typesetters right from the time when computers were first happening and so on, and people were typesetting onto them. And so people had quite big aims right from the start. And I'm starting back in about 1964, near the beginning of these things. This is not the first markup language. 1960s. One of the interesting things is that many of these are still being used. This is a list. This is not just draw me at 17 points in dark black. So there is an overlap there. I have one format I talk about which is purely semantic, but mostly things are somewhere in between. Separate to that, and independent, we've got two other concepts that we'll come across. One is lightweight markup, where you're not having to, where you can concentrate on the text. The actual markup you put in is a background task, it's not very obvious. And the other is perhaps the possibility of programmable texts, where your actual text is a program, you run it, and you get a document. And that may sound odd, but you'll actually find you already understand.
That's what LaTeX is.
So even at the very beginning of our timeline, though, people had quite sophisticated needs. We had phototype typesetters right from the time when computers were first happening and so on, and people were typesetting onto them. And so people had quite big aims right from the start. And I'm starting back in about 1964, near the beginning of these things. This is not the first markup language, but it's the first that's easy to find out about. And it's interesting because it's a precursor of others. This is a thing called Runoff, and it was invented by someone called Jerome H. Seltzer for the compatible time-sharing system. Computer historians will go, ooh, I know that. The interesting things that are going on here are every line that starts with a dot is a command. You're not like to start ordinary text with a dot, so that's quite a nice thing. This was capable of doing things like pagination, of doing left and right alignment, of centering text. All of these are tasks that if you're working with a teletype or a typewriter-like instrument, they're possible to do by hand, but it's really boring. It's much nicer to put in regular text and have someone else center it and align it. Also, commands like list and list element, which were in this thing right from the start, could be abbreviated to ls instead of list and le instead of list element. So we've got a lot of the constructs that we're familiar with are already here, and we've got the concept of abbreviation and of being able to determine which bits of the command and which bits of the text we're interested in. You could also have commands that you could put in the text to shift it in and out of other cases, and they use cases to mean things uppercase and lowercase, but also for other purposes as well, anything where you want to change the typeface. Later on this was ported to BCPL and the Multics computer system, and it's actually the ancestor of all of NROF, ROF, and all of those things that many of you may have come across. And also a thing called digital standard runoff, which I used in the 1980s quite a lot. And I wrote a bibliography of Joe Naken, a children's author, back then. Unfortunately, I don't have the sources because I didn't have access to runoff, so I converted them to HTML and didn't keep the originals, otherwise I'd have a nicer example. In 1969, Charles Goldfarb, who's known as the father of markup languages, and Edward Mosher and Raymond Laurie came up with a thing called GML, which stands for Generalized Markup Language. It also stands for their initials. They worked at IBM and wanted to make sure that they didn't get forgotten and lose the credit for having come up with this. And their idea was that you shouldn't just define a markup language, but you should define a way of defining a markup language. So here at the top, we have a DTD, which is a definition of markup. The triangle, you'll recognize this layout, it looks very much like HTML, and there are reasons for that. So this is saying we've got an element and a list, and I have to look at my notes for this. We're defining a list. The two hyphens say that we can leave off the start tag and we can leave off the end tag, they're optional. And the plus means that there must be at least one item element. And then below that, we're saying that an item. So the minuses mean that there must be, the O's in the item say that the indicators that this list item are optional. So you can start a list, and then you can immediately put a paragraph, and that text will be a list item. And we're saying that we can have PC data, which is text, or another list inside our list. So we've got nested lists defined. And then we've got the example below. Now, a lot of languages then were based on SGML. The very original versions of HTML came with starter sets. You didn't have to start down by writing your DTD initially. They came with useful ones right from the beginning. But the very first versions of HTML, for instance, were an SGML language. And a lot of that, and that's why this looks very familiar.
You know, I was just realizing the mistake I made with the HTTP parser, or with ophttpd at first, was going straight to writing a parser, and that's exactly the mistake I'm making here. What I want to define first is the intermediate language. Okay, and then worry about the parser later. Okay, yes, okay. That's the mistake I'm making with TextXX. Okay. So okay, so it's converting to XML. Okay, and then, okay, okay. I'm gonna, how long have I been recording? Because I'm starting to feel like I need a break. How long am I going to go on? About 2 hours. Okay, that's about right for a break time. Let's, what should I do? Let me, let's power through this. Power through history of text markup languages talk. Kernighan talk. TAD lecture. This looks really interesting, this virtual machines thing. It's going to have to wait. This looks important. Yeah, we'll add to my list of playlists. The Russian dude. He has a different one on parsing and compiling. Okay, I feel like I have an understanding of parsing. Okay, and then the parsing algorithms thing. That was bothering me. I don't really care that much about the parsing algorithms. Oh, he's fucking paywalling this shit. Fuck this guy. Fuck this guy. Never mind. Yeah, fucking pay. Fuck that guy. I'm not. I mean, I understand you gotta make your Semitic metal, but I don't have time for that. All right. I think it'll be the Finnish dude. Finnish dude. Okay, and then the MIT. And then MIT SICP lectures, which I think will go with the book. So I think we'll be reading both of those. All right, what else do we have? Read that looks important. Much later. Oh, this is from earlier this year. I think I watched this.
Even with all the time given up to me now by lockdown, there still isn't enough time. It takes forever, and it's a good job I'm semi-retired from being a part of the School of Computer Science at Nottingham, because honestly, as a regular employee, I could not justify the hours I've spent on my latest ultra-fascinating project. I refer you, my dear Watson, to the strange case of Dennis Ritchie's missing thesis. We all know who Dennis is. Unix was invented by Ken and Dennis. Ken Thompson, Dennis Ritchie. If you want to simplify things, Ken was sort of in charge of Unix, the operating system. Anything to do with creating C language facilities and C compilers. Because remember, Unix was one of the very first operating...
Okay. Brailsford. Ritchie. I know this is a distraction, and I know that this is doesn't seem like it's related, but it is related, because fundamentally every computer program is a compiler, and so I'm at the point where I'm butting up against my lack of knowledge in this, and so I just gotta learn about it, and we'll see how much time I can spend on this. Anyway, gotta watch this.
The concept of defining your documentation so that you can parse it in a program without having to quite know the meaning was very important development. Going on from the runoffs, in the 1970s and onwards, the ROFs came about. That's a very obvious derivative of the name for Unix typists who don't want to type anything letters. So we've still got the dot meaning a line, that's command. We've still got the long form commands, but no one uses them, everyone uses the short abbreviations. We can see here, this is a man page. It's not a real man page, but it's an example of a fake man page. We can see partway down that we've got headings, we've got subheadings. The /FB is saying change case into bold, and then the /FR is saying change case into regular. So we've got to state characters in our text to say what font we should be using, essentially. The innovation of the ROFs was to say, we've got nROF, which allows to terminals, it'll give you monospace type. We've got TROF, which allows to typesetters, it will give you proportional type. TROF has extra commands to do things you can do on typesetters, or photographic typesetters that you can't do on terminals.
Public domain, okay. What language is this? Perl. Okay, I'm going to bookmark this. Oh, This looks important. I'm going to subscribe and bookmark that guy. I already subscribed, didn't I? You know what a monad is. Lamport, this looks important, but I just don't care right now. I feel like listening to Lamport talk. Oh, Microsoft Research, of course. They hire all the brilliant people so that other people can't. Alright. I like this guy. I will put this in my watch later, which I never ever do, but yeah, this. Okay. I know I've watched this before and really enjoyed this talk, and so I want to watch it again. This.
The following content is.
You look at how many transistors are on various processor designs. Up until about 2004, we had Moore's.
Let's just watch this.
NROF will ignore them. So you can write the same text and have it output to more than one device by running different programs on it. So this is, in many ways, one of the first ways of doing device-independent output and having something that will nicely ignore what's going on. You can also run the macro processor over this, and so you can write macros that will automatically get turned into more complicated to-mark commands. The current contender for the field of ROFs is GROF, which is GNU ROF. It has a rather good documentation, so while the learning curve for all of these commands looks quite steep, the modern documentation for it is rather good. I don't personally use ROF anymore, but in my extra notes there's a good discussion between someone who uses TeX and LaTeX and someone who uses GROF, saying why they might use one or the other and why both are rational discussions. Which leads us to TeX and LaTeX. Does anyone in the room not know who Donald Knuth is? So, for example, if you don't know Donald, okay, right. When you go home, look him up. So, back in the 70s, Donald Knuth had written some seminal works on how to do on the theory of computer programming, and he'd written up, and this had all been typeset, and that was all wonderful, and he came to rewrite it, and he didn't have access to the technology he'd been using, and the copy editors kept coming back, and his equations were all wrong, and he got really upset. So, being who he is, he went away and wrote a program that would allow him to typeset his own equations correctly. And then he discovered there weren't any fonts he liked, so he went and wrote a program to allow him to create digital fonts, and then he had to create a digital font using that, and by this time a few years had passed, and then he went back to writing book again. His career has been like that. He's a polymath, he's fascinating, he's done all sorts of things. Relatively recently, in the last few decades, he taught himself to play the organ. In the last year or so, he's just produced a semi-mathematically created piece of organ music, a huge thing that's based on revelations from the Bible, because he's also a Bible scholar. He's a fascinating person, he has all sorts of wonderful stuff. Go and look him up. Anyway, that's nothing to do with this talk. So he created TeX to allow you to type, to have control over the exact typesetting of your document, down to the level of exact placement of pixels on the page if you wish, but typically you're not worrying about anything better than spacing. He also invented the first really serious paragraph and pagination algorithm, so that most of the time the program will lay out your text, you don't have widow lines, you don't have bits of text in the wrong place, paragraphs that should stay together can be told to stay together, and it will work it out. If you've got sidebars, you can say what they should and shouldn't be near, and it will magically work. This was all brand new, and he wrote it all up. He also invented literate programming, where you write your program, and you write your documentation, and you interleave them, and you have a program that pulls out the program and puts it back in the right order, because discussing a program, you don't necessarily want to talk about it in linear order. And that meant that the first version of TeX was written in one language, the next version of TeX was written in an entirely different language, but it was easier to port because the documentation existed, and so on. So this was driven by the need to do accurate typesetting of maths, but was very low level. If I was wanting to do a list, I would have to use the blob command, and I would have to say I want to use the blob command, and I want to put a text. So I'd write a macro to do that, and I'd have to write it myself. In about 1983, Leslie Lamport, who's a very well-known mathematician in his own field, wrote LaTeX, which is a set of macros on top of TeX that make it easy to use. So this is an example.
Damn it, where was the Biscuit? What was the one I just had here? Libraries. Here we are.
LaTeX from the fanzine I created many years ago. This is in text, someone who wrote the fanzine. This is much easier to use. The backslash command, curly braces around arguments, is very common. The backslash EM, because competence, you can see there saying if this is emphasis, it's clear which bit is being emphasised. The three hyphens together mean that's an M, between protagonist and A means that's an M dash. Two hyphens would be an N dash. One hyphen would be, I'm probably doing maths and it's just a hyphen. You'll notice that around the competent hero up there, so I'm pointing at my screen, I should be pointing up there. Around the competent hero, you've got a back tick meaning an open quote and a vertical tick meaning a closed quote. So this is an attempt to say, we've only got Ascii, how do we do quotes? We want to indicate which is which. Even if smart coding was available, we wouldn't trust it because it would get it wrong sometimes. So this is a person who really cares programming language for text. And it is a programming language. This is a program. It's a macro program, but it is. LaTeX is still dominant in maths and scientific documentation. I used to write my CV in it once upon a time, or actually in TeX, but this is a thing called TEI. I only found out about this when I was actually researching for this talk. This is a purely semantic markup language. This is used for marking up bodies of English text or any other languages to say what their meanings are so we can extract information about them here in them. So this is a markup of Swinburne's sestina part of it. So we're saying at the top that this is a sestina. It's a type sestet. The rhyme scheme is A, B, A, B, A, B. Clearly they have marked the rhyming word at the end of each sentence. They've marked whether it's an A or a B. They're giving an ID, A, B, C, D, E, so you can refer to them back from the text and say what they are. So this is a text that's been marked up to be analysable, you can do stuff with it. There are a heck of a lot of different markups in the TEI project designed for different purposes. I desperately looked to see if I could find a limerick, because that would have fit on the slide much better, but I couldn't find anyone who marked up a limerick in a way I could steal. This is still heavily in use, not in a field I have any knowledge of, but it's fascinating. I like reading documentation by people about things they're fascinated about, and there's a ton of...
I just realized, so HTML, we call it in the industry formally, it's AIDS XML. And then what we're going to call the thing right before we get to AIDS XML is HIV XML, which is the intermediate stage before we get to AIDS XML.
1991 is a really busy year in markup. So first of all, we have HTML. Now we can see at the top of this, doc type HTML. So this is HTML. This is an HTML application language. And one of the ways you can tell that is in original HTML, you can have arguments with people about whether the triangle P triangle is a separator or not. Because when you start body, it implicitly says, well, if you don't say, the next thing will be a paragraph. And when you start a paragraph, it implicitly closes the previous paragraph. So it's quite possible for someone to have learned that you start body, and then some text, and then a P, and then some text, and then you stop your body, and that looks like P's are separators. But this is just HTML being clever and having implicit rules. There is no version 1 of HTML, by the way. There's a version 2, but they didn't bother to name the first version. Why would they? So this was Tim Berners-Lee at CERN in the 1990s. HTML2 was published as an IATRSC in 1995, so that's the first time it was really formalised rather more thoroughly. And as of HTML5, it's no longer an HTML document type. Now it's its own thing. They've abandoned HTML. HTML is now sufficiently sophisticated just to have its own documentation of how it works without referring back to HTML. And in fact, HTML has begun to be abandoned because it's very complicated to implement the D2T understanding or throw away, and most formats don't need it. In the same year, we got DocBook. So DocBook has a lot of the semantic characteristics. We are marking up documents to say what the things are. So here we're marking up article info. So we're not just saying this is the author and the date and so on. We're saying this is the information about this article. And we're clearly marking sections and so on. So if you remember the talks before about structuring your documents so you can find things in it, DocBook is very heavily designed to enable you to find things. It's got a lot of use in industry and the military for marking up huge documents that might be talking about aircraft parts or things like that, where searchability is really important. And so far as I know, it's still used heavily in that sort of environment. It's also used a lot in the open source world for documentation because it's so versatile. DocBook originally was an HTML, but we can see that as of I think DocBook 5, it's become an XML format. So XML was originally it's an HTML document type that's saying we don't need everything in HTML. We don't need to have opening and closing tags being optional. It's a heck of a lot easier to program if they're required. It's parsers and simpler. Let's simplify down to what we actually need. And people like to say they hate it. And that's because it's quite complicated. But it solved a lot of problems. It stopped arguments about how should we lay out our text, because you've got no opinion otherwise, no good reason. You've got XML as a standard that is relatively easy to use and has very good library support. You can write programs to manipulate it very easily. DocBook obviously is in use today. In the same year, Ascii Text happened. Now, Ascii Text is very important historically. You will almost certainly not come across this. I don't think it's still in use. This came out of an online magazine for people using the Macintosh called Titbits. And the person didn't like SGML, and they didn't like HTML. They thought these were hard to write. Remember, back in the early days of HTML, people would write HTML by hand. You wouldn't try and do that now. It's too complicated. But in the early days, that was possible. So he wanted to write something that was plain text, reasonably readable, and could be turned into HTML for his magazine. So titles are underlined because you underline titles. Strangely, the body text has to be indented. I'm not quite sure why, except that it then means, so this is an error in Fortran, it's still relatively strong, and other languages where the beginning columns of your text still mean something. So you can see towards the bottom, by putting a triangle bracket in the left-hand margin, we're saying we want monospace font on this line. By putting a star in the left-hand margin, we're saying that we should have a bullet mark. By putting two dots in the left-hand margin, we're introducing a comment, or the very last line of the content can have two dots. This is also an error when people would mark this is the end of the meaningful part of the file, because the way file formats worked, you could have rubbish at the end of your file. So if you read your file and kept reading to the very physical end, you might find there was rubbish that just got in there, nothing to do with what you wanted. So it's common to have formats that say this is the end of the meaningful content. Bold words are two asterisks to mean bold, and close the same. Italic is twiddles, which is nice. Underlined words are also supported, so this is harking back to typewriters, where underlining, an actual physical underlining a word would mean italics. Here you're allowed to underline around it to mean italics again, because people are familiar with that. If you put backticks around something, that's saying, leave us alone. Don't. So if I went backtick, star, backtick, I get two stars out. Many of these things are influential to later formats, as we'll see. There's no documentation for this as such. There are some files written in Ascii Text describing bits of Ascii Text. I'm not aware of very many programs that will read it, so it's defined by what the author wanted for themselves. I don't know how many other users there were, but it's still influential for other things. This is the first wiki. So this is tremendously important in many ways. So this is Ward Cunningham inventing WikiWeb. Paragraphs aren't indented, thank you. So we've got list items and we can have sublists, but we can't have lists in lists. Indented text is monospace, that's quite nice. We have emphasis and bold and things. The rules for that are, one single quote means a single quote, two single quotes means the word is emphasized, three single quotes means it's in bold, five single quotes, that's 3 plus 2, means it's bold italic. And we've invented the camel casing to mean a link to another page, which is a very common wiki meme, it's very useful. But sometimes you don't want that, so if you put 6 single quotes after the first letter, then that will be not shown, but it doesn't make it, yeah. I cried when I first saw this almost. However, so we've got no HTML, no tables, no headers, no maths, no anything, no links within a page. We've got almost no typesetting. We're doing monospace, so if I want a table, I can draw a table with ASCII characters. This is deliberate. If you look at the content on the WikiWeb, it's all very simple discussion things. People writing simple text, they're discussing things. It's not for big, huge formatted documents. It's for people to have discussions about stuff using words. There isn't meant to be layout. If you use a list, that's a bit unnatural. So you shouldn't be using complicated lists. I think all of this is deliberate. I think he realised that using single quotes, if you're using 5 single quotes, you probably shouldn't have. But you haven't got escape characters to worry about. All of the rest of your text is just propagated through. So really weird things you wouldn't do, naturally, are how you mark things up. This is something I think he did brilliantly, and every wiki inventor since has not quite realised why. And the lesson they've taken is, well, actually, how markup works isn't important. And also, we want to do more complicated things in our wiki. We don't have an example of how to do that, so we'll just invent something, and we won't look up the history of markup languages. So my advice, if you're writing a new wiki from scratch, perfectly reasonable thing to do, don't try and be clever and follow Ward Cunningham because you don't have his design sense. Use Markdown, because someone has already designed something. And we'll get to why I have reservations about that later, but that's... So as I say, my initial reaction to all these quotes was to cry, but actually, I think later on I decided it's brilliant. So design can be carefully constructed and look very strange. This is my home territory, this is restructured text. I will write restructured text without thinking, partly because I was around when it was invented. A gentleman called David Guja, and I use gentleman advisedly because I believe he is a gentleman, I believe he's a very nice person, basically provided, the doc sig for Python was looking for a way to do documentation that was better than the preceding examples, which were mostly poorly documented, had buggy code and so on. And he provided a solution that we kind of ignored for a bit, and then we looked at him and went, oh look, here's a really well standardly documented answer that does almost everything we want in a coherent and easy to understand way, with reasons for why. So the principles of restructured text follow the principles of Python. The first thing is readability of the text. So the first thing is that restructured text, when you write it in your text file, should be readable. So you should be able to read it. That means compromises. So we have underscores for headings, we have body text, we've got stars for emphasis and so on, 2 backticks for teletype for font type. It's because we use single backticks to prove things for footnotes and links and so on. We've got footnotes because the second thing is we're output agnostic. We want to be able to output anything, not just to HTML or whatever. David had an SGML background, a big documentation background. The other thing is that restructured text very firmly says you can do so much, and then we stop. If you want to do something more sophisticated, use a more sophisticated language. Go to DocBook, go to something else, and that I think is quite important. And the other thing is, you'll notice in the list text follows the line of the actual text that's on the start line. It doesn't follow the line of the hyphen or anything else. So it's all nicely laid out. It's meant to be easy to read, as if you were reading an email that was well laid out. Ascii Doc takes a different approach. It says, well, we have DocBook. DocBook is wonderful. I tend to agree with that. But you'll spend so much time putting in these markers with triangle brackets around them that you can't see the text. So if you want to write text, DocBook is great for giving you the abilities, but it's hard to write because you can't see what you're doing. So let's have something that's easier to write, DocBook, and also marginally, quite a lot easier to read. It gives you all the power of DocBook. And in fact, you can have DocBook code in here if you want as well. So this is a tool for writing DocBook easily. So its compromises are different. We've still got headings. In fact, you can I believe you can do headings with underscores or with markers at the front, like you'll use with Markup. And that's again because different documents will look better in different styles. So here we've got underscores for italic. That's not unreasonable. We don't have underscores for italic in restructured text, partly because underlining text is a bad thing, but partly because underscores are syntactically meaningful in Python. And if we want to talk about Python code, having to escape underscores would be really awful. That's not relevant here. Paired plus signs for monotype? Yeah, interesting. You'll notice that where it says this is a list item as well, we've then got a plus sign. The plus sign is to say, well, I think this is to say, and the next paragraph continues the list. I think the thinking here is that most lists should be short declarative things, so it's rare to carry on to another paragraph. So let's make that the odd case and be explicit that we are counting this on, and then we can lay it out like this. Now, another thing to note here is footnotes. If you're writing text to be readable as text, you want your footnotes and your links and things to have something simple and the complicated bit somewhere else. If you're writing stuff and want it to be easy to write and to maintain, then you want your footnote in line where the body text is. So Ascii Doc very sensibly does that. And because it's going to DocBook, whilst it's technically not output agnostic, it's going to DocBook, it can go to anything that DocBook can make. So in practice, it's output agnostic. So this is the place you should go if restructured text is not complicated enough for you. And I should note that it's not entirely dissimilar, so if you know one, you probably almost know the other, and you should be able to write text that's very similar, or even the same, both of them. And this is my final slide about markup formats, my final like markup is Markdown. And I get so disappointed here. Markdown should have been so wonderful. So Markdown is really good, I recommend it. But, so John Gruber came up with Markdown as a way to write HTML more easily. And that was a good aim. He's not the first person to do this. I would argue he's done the best answer so far. But he didn't document very thoroughly. So his documentation of Markdown is lightweight, is a bit light, it's not very specific. The informational implementation was buggy. And he doesn't do a lot of things that people actually want. And these, together with the fact he didn't maintain it, mean that there are lots of variants of Markdown. So you can't say Markdown, you say GitHub flavoured Markdown, GitLab flavoured Markdown, or whatever. That's a problem. Also, you can include HTML, which means that it's a bit awkward sometimes to tell what things will turn into. And I think it would have been better not to include HTML and just say we are exactly this simple. However, all that notwithstanding, I point you at Common Mark, which gives you a huge document, which gives you exactly how Markdown works. It's huge. It's the biggest document ever. It's also very good to read. It's really well written. I still think that Markdown is a really great thing. I'm really glad he made it. It's the default thing you should go to for your users if they don't need complicated markup. And as I said, for wikis, gov.uk uses it for their input format. It's the obvious answer. And that's it. I've done a quick dash through many things. The notes online have a lot more pointers into Google, and I hope that was useful. Feel free.
How does this make file work? Okay. Powered through this. Okay. That was a good talk. Did I upvote this? I meant to, yes. And I'm gonna... Should I subscribe to this? Alright. I feel like I should go for take a break. I know I haven't done any actual work, but this is research. Alright, I gotta go. I'm gonna take a break. See ya.